Support vector machines, SVMs, are a powerful and versatile tool in the field of machine learning, particularly well-suited for classification tasks. At their core, SVMs aim to find the optimal boundary, or decision hyperplane, that separates data points belonging to different classes. This boundary is chosen in such a way that it maximizes the margin, which is the distance between the hyperplane and the nearest data points from each class. These closest points, known as support vectors, play a critical role in defining the hyperplane and consequently the classification model. The fundamental idea behind SVMs is rooted in geometry. For linearly separable data, SVMs seek to construct a hyperplane that not only separates the classes, but does so with the greatest possible gap between them. This ensures that the model generalizes well to unseen data, reducing the risk of overfitting. In cases where data is not linearly separable, SVMs employ a mathematical trick called the kernel trick. Kernels transform the input data into a higher dimensional space where a linear hyperplane can effectively separate the classes. Popular kernel functions include the radial basis function, RBF, polynomial, and linear kernels, each suited to different types of data distributions. Another strength of SVMs lies in their ability to handle noisy or overlapping data through the introduction of a soft margin. The soft margin allows some misclassification by introducing a penalty term in the optimization process controlled by a parameter known as C. A smaller C value allows for more flexibility and tolerance of misclassified points, favoring a simpler decision boundary. Conversely, a larger C value seeks to minimize misclassification at the cost of potentially overfitting the training data. This balance between complexity and accuracy makes SVMs highly adaptable to various datasets. In practice, SVMs are widely used in applications such as image recognition, text classification, and bioinformatics. Their ability to work well even with high-dimensional data and relatively small sample sizes makes them a popular choice in many domains. However, they may require careful tuning of parameters like the kernel type, C, and other hyperparameters to achieve optimal performance. Additionally, while SVMs are computationally efficient for smaller datasets, their training time can scale poorly with very large datasets, especially when complex kernels are involved. Overall, SVMs remain one of the most robust and reliable classification algorithms, offering a blend of mathematical elegance and practical utility. By leveraging the concepts of margins, kernels, and regularization, SVMs provide a solid framework for tackling a wide range of classification problems with both precision and versatility.